How do PV diagrams visualize closed system energy? Imagine watching a graph come alive, showing how a system changes shape as it moves through different states. That's what a PV diagram does in thermodynamics. It's a simple but powerful tool to see how pressure and volume interact during various processes. When we talk about a closed system, we mean a container where no mass enters or leaves, but energy can still flow in or out as heat or work. The PV diagram plots pressure on the vertical axis and volume on the horizontal axis. Each point on the graph shows a specific state of the system, defined by its pressure and volume. The path connecting these points reveals what kind of process is happening. For example, if the line is horizontal, the pressure stays the same while the volume changes. That's called an isobaric process. If the line is vertical, the volume stays constant but pressure changes, which is an isochoric process. When the curve shows pressure and volume changing in a way that temperature remains constant, it's called an isothermal process. This produces a hyperbolic shape on the graph. If the process involves no heat transfer, it's called an adiabatic process, and the curve is steeper than the isothermal one. The most important part of the PV diagram is the area under the curve. This area shows how much work the system does or has done on it during the process. When the system expands, the volume increases, and it does work on the surroundings. This appears as a positive area under the curve. When the system compresses, the volume decreases, and work is done on the system, shown as a different area. Since work is a form of energy transfer, the diagram helps us see how energy flows in or out of the system mechanically. When combined with the first law of thermodynamics, which relates internal energy changes to heat added and work done, the PV diagram becomes a handy visual for tracking energy changes. Engineers use these diagrams to analyze engines, refrigerators, and other devices that operate in cycles. For example, the shape of a cycle on the PV diagram shows the sequence of compression, expansion, heat addition, and rejection. By calculating the area inside the cycle, they can find the net work produced and the efficiency of the process. So, in simple terms, PV diagrams make the invisible energy exchanges visible. They show how pressure and volume change during different processes and how these changes relate to the work done and energy transferred. This makes understanding the energy flow in a closed system much clearer and easier to analyze.